lesson, there are a number of definitions that we must first understand before we can move on and do examples. The first thing we need to understand is a state. So a state is simply a situation or a set of values. So some of the examples we saw or are going to see are about market share. So the state would be what percentage of the market one store has over another store. A state matrix is denoted as S sub n, where S sub 0 would be the initial state, S sub 1 would be the state after one transition, S sub 2 after two transitions, and so on and so forth. And what the state matrix does is it shows the state of the system at any time n. And it may either represent the probability or proportion of the population that are in each state, or the actual number from the population that are in the given state. The current state is the situation or set of values at the present time. So whatever we have right now is the current state. The next state is the situation or set of values that results from multiplying the current state by the transition matrix. And we'll get into what a transition matrix is in just a second. But before we can understand a transition matrix, we first have to understand a transition diagram. So a transition diagram is a drawing depicting the various states and probabilities associated with a situation. So for this example that we're given here, our two states are sunny and rainy. So the probability that it's sunny on one day and that it'll be sunny tomorrow is this 0.8 right here. The probability that it's sunny today and will be rainy tomorrow is this 0.2 right here. The probability that it's rainy today and will be rainy tomorrow is 0.4. And then the probability that it's rainy today and will be sunny tomorrow is 0.6. Notice each state is represented by a circle. So sunny has a circle and rainy has a circle. The arrows show the movements between the states. So the probability of it being sunny tomorrow, given it was sunny today, that is 0.8, and that's that arrow. The probability that it's rainy tomorrow, given it was sunny today, is 0.2, and that's represented by that arrow there. Each arrow is labeled with the corresponding transition probability, and it's those transition probabilities that go into our transition probability matrix. And that's here. Transition probability matrix, and that's just the matrix representing the probabilities. The initial state distribution matrix is just a matrix representing the original proportions. A stationary matrix is a matrix that, when multiplied by the transition matrix, results in itself, and that goes along with the term steady state. So when you have a stationary matrix, you've hit a steady state where no change is occurring. The steady state of matrix S is a Markov chain is an eigenvector of the transition matrix T with an eigenvalue of 1. So there will be two eigenvalues for this steady state, but one of them is always 1, and we'll go into that a little bit more later. So what happens is there comes a time where, as we multiply over and over and over by the same matrix, finding the probabilities, there becomes a point where our probabilities approach a value where they're not going to change anymore. And that's what the steady state and the stationary matrix refer to. A regular Markov chain is what we're going to be studying here today. And a regular Markov chain has a regular transition matrix. And a regular transition matrix is one that will approach that steady state. So everything that we're going to deal with will have that steady state. Not all Markov chains do, but for our purposes, what we're studying in this unit will always have that. And a transition matrix P is regular if some power of P has only positive entries. So does every Markov chain have a unique stationary matrix? The answer is no. Okay. If a Markov chain has a unique stationary matrix, will the successive state matrices always approach this stationary matrix? Not necessarily, but if it's a regular Markov chain, then the answer to both questions is yes. So properties of a regular Markov chain. So let P be the transition matrix for a regular Markov chain. We find out there's a unique stationary matrix S that can be found by solving the equation S times P equals S. So our stationary times our probability gives us back our stationary. So given any initial state matrix S sub 0, the state matrices S sub k approach the stationary matrix S, and the matrices P raised to the power of k approach a limiting matrix P where each row of P is equal to the stationary matrix S. So what happens is we raise P to a really big power, and we can also find our stationary matrix that way. So one way we can do it is by solving a system of equations, which we'll see. The other way is raising our transition matrix to a very large exponent, and that will also find it. For our first example, we have an electrical company is working on a large commercial construction project. At the end of each day, the workers typically leave equipment on either the current floor, the roof, or in a storage room. The foreman observes that at the end of one day, the distribution of equipment was, so this is our initial state, so it's S sub 0. So 70% of the equipment was on the floor, the current floor, 20% was on the roof, and 10% was in the storage room. And he considers whether this transition matrix here might model the distribution of the equipment from day to day. So he's saying, okay, well, you know what? 80% of the stuff that's on the floor is going to end up on the floor again tomorrow. 10% of the stuff on the floor is going to get switched to the roof, and then 10% of that stuff on the floor is going to get switched into a storage room. And then this continues. So this means that for here, 40% of the stuff that's on the roof gets put on the floor, 40% of the stuff on the roof goes back on the roof, and then 20% of the stuff on the roof goes in a storage room. And then lastly, 40% of the stuff in a storage room ends up on the floor, 30% of the storage room gets put on the roof, and 30% of what is in the storage room goes back in the storage room. So putting these in our calculator, I'm going to put my S sub 0 in first. So I'm going to do second matrix. I'm going to go over to edit. I'm going to choose option A, and I have 1 row and 3 columns. My probabilities are 0.7, 0.2, 0.1, and now I'm going to fill in my second matrix. So second matrix, I'm going to go over to edit, go down, and this time I have a 3 by 3. So now I have 0.8, 0.1, 0.1, oops, that's 0.4. I'm ahead of myself. Now I have 0.4, 0.4, 0.2, 0.4, 0.3, 0.3. Okay, so I'm just going to double check this before I move on. 0.8, 0.1, 0.1, 4, 4, 2, 4, 3, 3. Okay, and you'll notice that my rows add up to 1 because those are the probabilities where everything could be left. So my rows add up to 1 here. So that's another good way to double check yourself to make sure everything's right. So the first thing we want to do is find S sub 1. So in order to find S sub 1, I need to quit to go back to my main screen. I'm going to say, okay, second matrix. I'm going to do matrix A times matrix B. When I multiply these together, now I find out that my S sub 1, so at the end of the first day, I now have 68% of the equipment is on the roof, 18, or no, I guess that was the floor. 68% of the equipment is on the floor, 18% is on the roof, and 14% has made it into the storage room. So now from here to find S2, I keep that answer and I just say, okay, I'm going to take that state, the state at the end of day 1, and I'm going to multiply that by my matrix again, so matrix B. So now at the end of day 2, 0.672, no commas, remember no commas in matrices, 0.0182, 0.0146. So we see that there's already not much movement off of here. So now we want the end of day 3. So now at the end of day 3, I'm going to take my answer from day 2 and I'm going to multiply that by my matrix again. So now I have 0.6688, 0.1838, and 0.1474. Okay. And now I want at the end of 10 days. So I could keep doing this and multiplying and multiplying and multiplying and multiplying, but between 3 and 10, I've got quite a ways to go. So instead, what I can do is I can go back to that first matrix, so my matrix A, and I'm going to multiply that by my matrix B. But instead of just doing B, I'm going to do B raised to the power of 10 because I'm going to essentially multiply by B 10 times. So raise it to the power of 10. And now these are my answers. So I'm going to round these to 3 significant figures. And now you can see how there's the little arrow on the right-hand side. I'm going to have to arrow over to the right to figure out what that last number is because the decimals are so big it didn't fit on the screen. And once again, remember no commas in matrices. It looks like I threw an extra parenthesis up in that one. 0.148. Okay, so find the steady state if there is one. Well, it looks like we've kind of already found that steady state. If you look from S3 to S10, not a lot of changes going on. But what we can do is we can say, okay, you know what? I'm going to take my matrix A, what I started with, and I'm going to multiply it by my transition matrix. Let's try 100 times. Let's see if the calculator can handle 100. It might not be able to handle 100, but let's see what happens. Let's see if it'll do B to the power of 100. And you'll notice it appears to be the same numbers we just had. And remember, we talked about how the 3 numbers have to add up to 1 because that's our 100% of the equipment. So since our first 2 numbers are the same, even though I can't see my third number, I know that one's also going to be the same. So my steady state, if there is one, so I'll do S sub S for steady state, would be the same thing. Now, due to slight rounding, these might not always add up to quite 100 or 1 because of the rounding to 3 sig figs, but it's going to be pretty close. And in this case, it works because 6 and 7 would be, 7 and 8 is 15, and another 5 is a 0, so it looks like it's all going to add up to 1, and we will be fine.